Okay, so we're solving a multi-block pulley inclined plane physics problem here. We're going to find the acceleration. So we have an 8 kilogram block sitting on a table. We have a plane here that's inclined at 35 degrees. That's 35. Draw it in so you can see it a little bit better. We've got light pulleys. We've got string, a 20 kilogram block pulling down here, and a 12 kilogram block pulling down there. And the question is, what is the acceleration of this system? So the simplification I like to do with these is I draw an analogous block, a single block, and I'm going to draw all the forces acting on this block, and it's going to have a total mass of the combined mass of all of these blocks. So gravity, as it pulls down here, will be an arrow on the block going to the right. As it pulls down here, will be an arrow going to the left. This tension will not show up at all because I'm only looking at what happens to the system as a whole, not the forces within the system. It'll have an overall mass of what's combined here. It'll have gravity pulling here. It'll also have gravity pulling here. Friction is happening not within the system, but to the system. So the force of friction happening on the 5 and the 8 are going to show up here as well. To figure out which way to put the arrows for friction, all you have to do is basically guess which way the system's going to go. By the looks of it, I've got a 12, I'm pretty sure, I've got a 12 kilogram mass pulling down here, an inclined plane here. The system's going to go to the right, or you could say clockwise. However, if my guess is wrong, I'm going to end up with friction going in the direction of motion. And that's going to be the indicator to me that I've guessed wrong. Okay, so let's get started. So the first thing I'm going to put on here is going to the right. So to the right will be clockwise. And going to the right, I'm going to have 20 times 9.8. That's the force of gravity pulling this block down. I'm also going to have the perpendicular component of force pulling this way. And I'll draw it out so we can quickly figure out what it is. We have gravity pulling straight down. So we have a perpendicular and parallel. It's the parallel component I'm looking for. Sorry, I said that wrong. We have a perpendicular and parallel component of force on this block. And as that's 35, in here will also be 35 degrees. The actual force due to gravity on this is 5 times 9.8. So the force of gravity that is parallel to the plane is 5 times 9.8 times the sine of 35. So this is 5 times 9.8 times the sine of 35. I'm also going to have, no, that's it. That's everything pulling this to the right. Pulling it to the left, I'm going to have gravity on my 12 kilogram block. So that's 12 times 9.8. I'm also going to have the force of friction from block 8, and I'm going to have the force of friction from block 5. And we'll calculate those in a second. Remember, the reason why we're drawing the friction arrows this way is the assumption we are making is that if there's no friction at all, or with the given amount of friction that we have, that our system is moving this way. Remember, friction opposes motion. If that guess was wrong, if indeed the system is going to go the other way, that's going to show up here by predicting an acceleration this way, which means we have a net force this way, and assuming this started at rest, we have motion this way. As soon as my diagram tells me that motion and friction are in the same direction, it's wrong. And once we realize that, then we adjust it, we switch the arrows, and we recalculate. But I don't think that's going to happen here. Okay, so again, everything pulling this in the clockwise direction is gravity on this guy, that's this arrow, gravity on this guy, but the component parallel to that plane, that's this arrow. And that's everything that will pull it this way. Everything pulling it the other way, the friction on this block, which is opposing motion, so I'm drawing it here. The friction on this block, so I'm drawing it here. And gravity pulling down on this block, and I'm drawing it here. Okay? Our total mass is 20, 32, 45. 45 kilos. Okay, the force of friction on block 8 is quite simple. The force of friction is 0.2. That's on block 8. Is 0.2 our coefficient of friction times our mass of 8 times acceleration due to gravity, 9.8. If you need further explanation, you shouldn't be on this problem yet. You should learn that and then come here after. So our value there is 0.2 times 8 times 9.8 is 15.68 newtons. So I've got 15.68 newtons of friction on block 8. That's this guy here. And the force of friction on block 5. Force of friction on block 5 is going to be the normal force, which is 5 times 9.8 times the cosine of 35 times our coefficient of friction, which is 0.1. So this is 5 times 9.8 times the cosine of 35 times 0.1. And that's 4. I didn't plan for it to come out that simple, but that worked out nice. It's 4.01. I'm going to round that to 4. Okay, so over here we have our force of friction on block 5 is equal to 4. Our force of friction on block 8 is 15.68. So 15.68, 4, and 12 times 9.8 are pulling the block this way. And 20 times 9.8 and 5 times 9.8 times sine 35 are all pulling the block that way. So I'm going to redraw it as just a single arrow each way, and then I'm going to subtract and redraw it again as just a single arrow, and then we'll easily have acceleration. So everything going to the right is 20 times 9.8 plus 5 times 9.8 times sine 35. So we've got everything going to the right is 224.1 newtons. Everything that's pulling it to the left is 12 times 9.8 plus 15.68 plus 4. And that's 137.28. So the net force is clearly to the right, which means the system is indeed rotating counterclockwise. Technically it's not rotating, everything's moving in a linear fashion. And its net force is 224.1 minus 137.28, and that's 86.82. And remember, our total mass of this block is 45 kilos. And if you learn anything in physics, it is that F is equal to ma. So our acceleration is going to be our net force of 86.82 divided by our mass of 45 kilograms, giving us an acceleration of 1.9 meters per second squared, and that is causing all of this to rotate to the right. So to recap, that's a great view of your gift card, Sam. So to recap, our system will move to the right, and the way we deal with it is we take our complicated system, but because it's all attached with... Yeah, good one, Sam. It's all attached with ropes.
How will cry?
It's all attached with ropes, so because of that, we can model it as a single block with several forces. Some of which go clockwise.
Some of which goes clockwise.
But we analyze it by drawing it to the right. And some of which are counterclockwise, including friction which oppose motion, and we analyze those by drawing them to the left. Say that, Sam.
Sounds very hard.
All right. So good luck with your questions.